your camera needs to work, the camera on your computer, and also your phone needs to work, because I need to be able to see your monitor at all times from your phone. Let me show you how is the setup. Let me see. So I'll run to, I'm sharing with you, I'll go to proctoring setup right there. And there is the picture of the proctoring setup. So a camera where you put your phone, and your phone is pointing at your monitor, because I need to make sure that you are potentially a student could go to ChatGPT. So I need to ensure that no student is on ChatGPT. So I need to be able to see your monitor. At the same time, I'm seeing your face through your laptop right there. So let me see. I'll grab this and bring it to our notes. There. Let me see. There. You might not have a phone, but then you need to use a second laptop, the camera of the second laptop, to be able to point at the monitor right there. Let me see. Copy and send it to your notes. There and notes. Let me see. Us, and that will be lecture 2, week 4, spring 2025. Of course, there. Let me put math 2305 right there. So perfect. And then I'm going to paste right there. So a way that you can make your right there, your phone stand, and make sure that your camera works. Like if your camera breaks or anything breaks during the exam, well, that exam will be replaced by the final right there. So make sure that your equipment is okay for a DLS class. I mean, that's what we assume a priori when we take a DLS class, that you have the right equipment to take a DLS class. So make sure that your camera works. In case that your camera is old, have a second camera in case that it doesn't work. If you disconnect from the exam, email me right away, because you need to connect back within 2 minutes right there. You cannot just wander for half an hour and come back. That makes the exam obsolete. That makes the exam a take-home exam. You just took it, you left, and then you came back. Can you see what I'm saying? I need to make sure that the test has security. Otherwise, the course is worthless if the test doesn't have security right there. Nobody will have trust in DLS, or nobody will have trust in online, and they will not have the courses as equivalent as a face-to-face. So it needs to be similar proctoring as a face-to-face. So perfect. Any questions on the setup for the exam next week?
So how am I going to log both the phone and the computer into the Zoom at the same time?
Do you think that you can only enter under one account? It's a one-to-one correspondence? No, I can have multiple Francis right now. Francis, you can be on your phone has Zoom, and you can be on the computer at the same time. Can you see what I'm saying, Francis? There could be 3 Francis. You could be on 2 laptops right there, and the phone. Can you see what I'm saying, Francis?
Yes, I can. Спасибо.
Yes. Okay, so we'll practice on Tuesday. So make sure that you have the equipment on Tuesday to do a mock, to make sure that I can see your computer, your monitor, and I can see you at the same time. So Yes, go ahead,
Move the
question.
camera toward my sheet and how can I look at the problems at the same time?
You are looking at you are looking at your computer. Your computer has a monitor right now. So you can look at the problems at the same time right there. Can you see that? You can look at the problems at the same time because you can view your monitor and I can view you through the camera in your laptop, but I can also view you through your phone from behind, from the side. Can you see that I made a little drawing there? Can you see that that individual that I draw right there, she can look, that individual that I draw right there in red, she can look at her monitor. Can you see what I'm saying, Ala? So it is possible, can you see? Yeah. And then you can write on a piece of paper that then, of course, when the exam is over, you will just take pictures with your phone, right there. So we will make a mock next class where we will assume that you end the exam, you take pictures, and you upload them. Okay with that? Okay, so we'll do a mock exam. One question. It will be, it's not graded, it's just a simulation of an exam on Monday for like 15 minutes. Happiness with that? Perfect, thank you.
The exam is going to be on Tuesday?
No, I just said that the exam, yeah, it's on the 20th, it's on the syllabus, it's on the 20th. But we will mimic, we will do the simulation on Tuesday. The simulation on Tuesday, the exam is on Thursday. Perfect, and it's from day 1 all the way to section 3.3. From day 1 to section 3.3. Okay, let me see. So I'll go right away and keep talking about proofs a little bit. Keep talking about more proofs right there. Let me see. There. Any more questions on the setup? Okay. So let me see. I'll put a statement right here. It's too wide. Right. There. Let x and y be rational numbers. Comma, if, that's it, rational numbers. Then x plus y is a rational number. Right there. So proof right there. So for all x and y rational numbers, comma, x plus y. I don't put the then. Let me take the then out. It's not a big deal, but I'll put a comma and make it look like a universal right there. The let is always a for all. The let is equivalent to a for all. And I'm writing this as for all x's and y's in D, comma, x plus y is in D. There, some property. So that's a universal from section 3.1 on the exam, right there. And also in chapter 1, right there are the universals also. So perfect. Of course, I can write it as a conditional. Let me just show you. that's equivalent to if x and y are rationals, if x and y are in Q, like that, with a double stroke right there, that's the set of rational numbers. A Q with a slash, like that, that's the symbol. Comma, then x plus y is in Q, right there. So happiness with that, they're both equivalent right there. Does anybody remember the definition of a rational number?
It's the quotient between two integers.
The quotient between two integers. Yes, a pleasure. What else would you like to tell me? But it's almost there. The definition is almost there. So perfect. Let me write the definition. So we will prove that, but let me start definition. Then we will write the statement again. Definition. X is a rational number means if and only if x is equal to a over b, comma, and then I actually need to say where a and b are coming from. A and B in Z. In the set of integers, right there. Perfect. And what else would you like to say?
B is not equal to 0.
Gracias. Perfect. B cannot equal to 0. And B is non-zero. So we're going to use that definition. So we are proving the closure of the rational numbers under addition. Right there. Remember that last class, we were not proving, we were using as an axiom that when you add two integers, you get an integer. We were believing that as an axiom. Let me just go and show you. So last class, if I go to Blackboard, we were utilizing this axiom. So I'll run to Blackboard for the integers. We were utilizing, let's go to our courses. I'll go to the course documents. And then my first entry is the axioms from 1904. Let me see. From piano, the piano axioms. Let's go right here. As course documents. And I'm sorry, 1904, 1889, there are the axioms right there. The axiom that I'm using is every natural number has a unique successor, which is a natural number. I'm sorry, they're saying natural, but they really mean, in this case, they mean positive integers. Right there, okay with that? So they're giving me the closure of positive integers, which means that you can keep adding. Can you see? Going for the successor is like adding 1. I can always add 1 and get another positive integer. I can always add 1 and get another positive integer. Right there. We know that since children. But of course, you need to say it. You need to have it it was there as an axiom from 1889. But let me give you, I will give you a better tool. I will give you a better tool than using the axiom in a minute. So I will give a better tool than Susana is using the axiom. Right there. Let me go back to our notes. But I was referring to this axiom right here. Because we will refer more and more to this axiom in the future. Let me see. I'll run to our class there. So that's it. Let me write the statement again. So we're proving the closure. Show that show that the set of rational numbers have closure under addition. Right there. So that means if x and y are elements of Q, then x plus y, it's an element of Q. So that's it. We start the proof like we did last class, right there. So we need to assume the hypothesis. So we assume the hypothesis, and right after that we have a definition. We'll use the definition. And after that we'll use algebra. We'll need to find a common denominator. And after that we need to use the closure of integers. Right there. We'll use closure. Of the integers have closure under sum. We'll use the axiom. I'll need the axiom right there. So here we go. Assume our first sentence. Assume x and y are rationals, are in Q. So I could have written it with symbols. By definition, let me enter some students there. By definition, comma, x, it's equal to A over B for A and B in Z, and B not equal to 0. Right there. Similarly, I'm going to say the same thing for Y. I'm going to say the same thing for Y. Similarly, Y, it's equal to what?
X.
C over D.
C over D, yes. Don't use A over B again. Yes. The proof needs to be general enough, so you cannot use A over B right there. So yes, Y it's equal to C over D. Perfect. Yes, thank you. C over D for some C and D in Z, in the set of integers, and D not equal to 0, right there. Now comes the algebra portion. Consider the expression x plus y, period. Can you see? I brought it in. I brought the expression in without saying anything. I'm not going to. I brought only the expression in, only that portion right there. So let me also emphasize this. This is the hypothesis. Which I better assume. Right there. And of course, everything is the conclusion. Right there. All of that is the conclusion. Don't bring the conclusion down. Only bring the expression. Right there. Bring only the expression. Unless you want to say to show that x plus y is in the rationals. Yes, you can bring it down then. But still, do not write only x plus y in the rationals. You will be assuming what you have to prove. So perfect. By algebra, we get, and that's it. We start adding x plus y. It's equal to a over b plus c over d. And then you just need to add the a over b plus the c over d. Right there. Common denominator. Then the common denominator divided by b is d. So d times a plus the common denominator divided by d is b, and that would be c times b. Right there. Happiness with that. I just added the fractions, the way that we add fractions in some grade level. I'm not sure which one, right there. But I just added in the abstract, I added the fractions, right there. Happiness, perfect. Now, what do I need to do next? I need just to say, I need to convince whoever is reading this proof that the numerator has to be an integer and the denominator has to be an integer. So next I will say, see that AD plus CB and BD are integers. Because the integers have closure under addition and multiplication. Have closure under addition. Under addition and products. Addition and multiplication. Perfect. What else do I need to do to convince somebody that is reading this proof that x plus y is irrational?
BD is not equal to 0?
Yes, b times d not equal to 0. Perfect. That's what I need to do next. See that? To conclude, see that b times d is not equal to 0 because b is not 0 and d is not 0 above. Right there. Remember, all the way up here. B was not 0 and D was not 0. That is called the zero product property. That's not always the case. Let me just make a note. I'll make a note at the end. I can say this about recall that the set of integers have a zero product property, the zero product property. Thus, hence, x plus y is a rational number. So, again, let me put the box right here. The skill of test 2 and test 3 and so on is to write proofs, to write complete sentences. So that's the theme of the entire course. That's the theme of that's the theme of the entire course. Let me any questions on this proof? Right there. So all the proofs that we write are formal proofs. So there is no such a thing as an informal proof. Every proof that we write is a formal proof. If not, you would have told me it's a JOT. J-O-T is a JOT that you do on the side. It's just a strategy, but it's not the actual proof. Every proof that we write is equivalent to a formal proof. Happiness with that. Now, let me talk a little bit more about the zero product property. Here comes the zero product property. If it's a property on a set. If for all A and B in some set S, comma, if A is not 0, oh, like this better, the contrapositive. If A times B is equal to 0, comma, then A is equal to 0 or B is equal to 0. Right there. That is the zero product property. There is the hypothesis. And then right here is the conclusion with an or right there. Happiness with that. Yeah. Two elements of that set or two expressions are equal to 0 when one of the elements is 0. Not every set, not every system, not every algebra has the zero product property. Not every system. Let me give you an example. Matrices do not have the zero product property. I can have the matrix A times the matrix B be equal to 0, but the matrix A is not the zero matrix, and the matrix B is not the zero matrix. Can you see what I'm saying? The set of matrices do not have zero product property. I just wrote the negation of the conditional statement that you have above. The hypothesis is realized, and none of those two. Let's try to make them up. Let's put a 2 by 2 matrix right there. It could be 1, 0, 0, 1 times 1, 0, and then another 0 here. That's not the zero matrix. And then I will put a 1 right there. And when I multiply, let me put this one here. There. That times that, that times that, that times that, you get the zero matrix. Check me on that right there. There. So, A is not the zero matrix, B is not the zero matrix, but now when I'm multiplying right here, that is 0, that is 0, that is 0, and that is 0. I did all the dot products between those two. Right there, they're 0, all of them, right there. So you have two non-zero matrix multiplying to 0. Happiness with that. So it's not that every system, every numerical system has the zero product property. It fails with 2 by 2 matrices. Okay with that? But the integers have it. That's why I use it. I had to use it right there. Okay, question. Okay, let me close. So, last class, I was talking about the closure. Let's say the closure of Z under sums, under addition. And I was saying that that's an axiom. Well, I have students that they don't want to feel, they do not want to use the axiom. They want to make a definition. Right there. And we have this definition called a binary operator. I mean, a binary operation. Right there. So let me give you that definition. So suppose you have a set S. Well, I'll write it as a definition. Let S be a set, a binary operation is a function f from S cross S to S. To S, right there. Let me write it right here. So that's it. F has as its domain S cross S and the codomain S, right there. This is the domain. And this is the codomain. Right there. So, can you see? So, have you seen binary operations before? Well, you need to come up with a set. You need to come up with an operation. And this needs to work. Look at the domain. The domain are order pairs, A, B. The domain are all order pairs A, B, where A and B are in S. And the codomain is in S also, right there. So now, by using this definition, I don't need to appeal to the closure of the integers under addition, right there. Look at this. I can have a binary operation on the integers. Z cross Z to Z, where F of A, B it's equal to A plus B, right there. The set of integers under addition are a binary operation. Can you see what I'm saying? The set of integers under addition. Give me a number. 2. Give me a number. 7. 2,7 is in the domain. They are both integers. And I'm going to apply addition. Addition is also an integer. Right there. Can you see? So right there, this definition, I can actually use it every time on all the proofs that I did. I can say, well, the integers are under addition. The integers are a binary operation. Right there. So that guarantees the closure. Can you see right there? Because having the binary operation, it better be the case that the codomain, which is addition, is also in Z. Can you see what I'm saying? So this is one of the best functions I learned in this class because it defines addition in a new way. It defines multiplication in a new way because I could have Z cross Z to Z where G of A comma B is A times B. So now I define addition and multiplication as a function. And this is a binary operation. A binary operation is a function. Of course, you can go later on and call this function. Nobody does that, but you can call this function the plus function instead of f. And you can call this function the star function, meaning make it look like multiplication right there. So happiness with that. I think that's really, really cool. That I can define addition of integers and multiplication of integers as a binary operation. So then they will have closure. If they are binary operation both, they have closure by definition. So I don't need to appeal to the axiom. I will say, on every proof that I've done so far, I will say, well, this item and this item are in Z because Z has a binary operation. We can construct the binary operation under addition and multiplication for the integers. Happiness with that? Perfect. Is division under the integers a binary operation?
No.
No, because you can put them together and you might get a rational. Yes. Realize that everything that I've done worked for the real numbers also. I could put the reals. Instead of Z, I could have put the reals. R cross R. So, perfect. Let me close. Right there. Okay. We need a definition. New definition. One of the most important definitions of the class. Divisibility. We say A divides B. A divides B. That is a vertical line. That is a vertical line right there. And it reads like this. It reads A divides B. So the line has to be like that. A divides B. So that means that A goes into B so many times. A goes into B so many times. So here comes the definition. A divides B means that B it's equal to AK. Let me write it in full splendor. B, it's equal to AK for some K in Z. I'm not saying it looks abstract. The first time I saw this, it looked abstract. But I'm basically saying that A goes K times into B. And that's what my second grade teacher told me. Okay, with that, this all looks abstract the first time that I saw this. But here is saying, what we're saying right there is that A goes K times into B. We are saying also that B is a multiple of A. That's equivalent to B is a multiple of A. And that, I put equivalent, but let me put same. Same as. And I'm going to say same as again. If B is a multiple of A, what is A with respect to B?
It's a factor.
Gracias, gracias, is a factor. A is a factor of B. Perfect. Perfect. So that is the new definition right there. So let me write it so we practice for the test. I'm going to write it as an existential statement. A divides B. I'll write it as an existential statement. A divides B means that there exists K in Z such that B is equal to AK, right there. So that is an existential statement, similar to the ones that we're going to see on test 1. Now, just to practice for the test, can you write the negation of that statement?
There is no K in Z such that B equals AK.
Oh, be careful. What you said it's okay, but you need to use quantifiers.
For all K in Z, B crossed out equals AK.
Perfect. Thank you, Francis. Yes. So here comes the negation. A does not divide B. So we have the symbol, slash the vertical line. Slash the vertical line means. And now exactly what Francis said. For all K in Z, comma, B is not equal to AK. Right there, perfect. So here we read this, read as A does not divide B. Right. A does not divide B. Perfect, perfect. So let's go and prove something. Let's go and prove something. If for all A and B in Z, comma, if A, let me write it better. For all, example, for all A, B, C, and D in Z, comma, if A divides B and A divides C, then A divides B plus C. Let me get rid of one of the letters there. There. I'll get rid of the D. I'll put a B anyway. There. For all A, B, and C in Z. Right there. Now, just to practice, we'll prove this one. But this is the true statement. So the negation has to be a false statement. But let's write the negation just to practice. So write the negation just to practice for test 1. So this is, and then we'll go and prove this one.
There exists an A, B, and C in Z such that A divides B and A divides C and A does not divide B and C.
Perfect, Francis. Yes. Yes. The universal becomes extension. That's it. Let's put the symbols. So what we have is this. For all X and Y in some domain D, comma, P of X, comma, if Px, then Qx. What Francis said is there exists X and Y in domain in set D where such that P of X happens and Q of A fails. Right there. The negation of the conditional. Right there. So perfect. I will write exactly what Francis said. There exists A, B, and C in Z such that A divides B and A divides C, but A does not divide B plus C. Can you see that the but is an and? Right there. A but is an and. It works the same way. Happiness with that. Perfect. Let's go and prove it now. We will assume the hypothesis and then do some algebra and arrive to the conclusion. What is the expression that we need to bring down? That is the expression that we need to bring down when we're doing the proof. So let me write the statement again. And that's the expression when I say consider, the expression will be that portion. So let's go for it. For all A, B, and C, in Z, comma, if A divides B and A divides C, then A divides the sum. Right there. So proof. Let A, B, and C be integers. B in Z. Integers, plural. Right there. Integers. Okay, also assume and then I need to assume the hypothesis. I need to assume that A divides B and A divides C. Right there. So then that's it. By definition. Comma. B, it's equal to AK for, by definition of divisibility. Let me say that sounds a little nicer like that. By definition of divisibility. Comma. A it's equal to B is equal to AK for some existential, for some K in Z. And what is the next sentence that I'm going to write?
Is it consider A divided by B plus C?
Oh, no. The next sentence, because I only did B equals AK. Now I need to do the other one, this one. Brendan, I need to play with that one. What would I say next?
C equals C equals AK.
No, I cannot say C equals AK. I cannot say that way. So we make sure that you write that you cannot say C equals AK.
C equals IL for some L in Z.
Yes. C equals AL. I need to change the K to something else. I cannot use K. I'm not allowed to use K twice. Right there. I need the proof to be general. But thank you for saying that because I needed to emphasize that. Thank you. Yes. C. I'll put it in red, in orange. C. It's equal to AL or AQ for some L in Z. Perfect. So I'm emphasizing that right there. I need to use another letter right there. Always. So perfect. Now comes the moment where I'm going to bring the expression down. Consider the expression and that's it. That one right here. I'll circle it. Only that portion. Consider the expression B plus C. Right there. Period. By substitution and algebra. By plug-in or by substitution. By substitution and algebra, we get and here we go. B plus C. This is the heart of the proof. Here comes the substitution. AK plus AL. Here comes the algebra. Right there. Okay, with that, I had to make all the moves. Next, I can appeal to the closure of the integers, or I can say that the integers that we have a binary operation under that addition is a binary operation. Okay, with that, I can say this. I'll say see that addition is a binary operation under Z. Thus, K plus L is in Z. Right there. So it's an integer. So then I can say hence A divides B plus C as desired. And put the little box, the little square right there. So I appeal to the closure of the integers and their addition through the binary operation. Through the idea that we have a binary operation that the integers and their addition have a binary operation right there. We have the existence of that function from Z cross Z to Z, which is A plus B. Happiness with that. You can do it both ways. Appeal to the axiom, which is the closure of the integers under addition, or appeal to the existence of the binary operation. Happiness.
This might be a dumb question. Why
No.
why do we care if B plus C is
I'm sorry. No B plus C.
or sorry,
I'm
K
sorry.
plus
So go for it. Yeah, Brandon.
why do we care if K plus Q is an integer if in the definition of divisibility only K was an integer and not A or B?
Oh, let me see. A or B. No, A and B are integers at the top of the statement. For all A, B, and C integers.
Now, I was looking at the definition of divisibility.
Yes. Brendan, a priori, A and B are integers.
Gotcha, okay, thank you.
Yes. So let me go there. I'll put the definition right here. Thank you for your remark. Let me see. I'll go right here. Let A and B be in Z, comma. A divides B if and only if B is equal to AK for some K in Z. Thank you for making that remark, Brandon. Now I have it right there. Perfect. It applies to two integers, and we are playing with integers. This is a portion of number theory. So we want integers. We're going to play with integers across the board for a while. These are all results from number theory. And they call it number theory, but because in the past number was only integer, right there. Okay. Right there. Transitivity. For all A, B, C, ABC, in Z, comma, if A divides B and B divides C, then A divides C. Right there. Happiness with that? The transitivity of divisibility. So let me write right here. This statement is the transitivity of divisibility. So proof. Let A, B, and C be in Z. Also assume the hypothesis. Assume A divides B and B divides C. So by definition, comma, B, it's equal to AK for some k in Z. And C, it's equal to BQ for some Q in Z. Happiness with that? Perfect. Now I'm going to bring the expression. It's not expression. It's only I'm going to bring this. I'm going to consider C right there. Next, or I can say by plugging. I'll go like this. By substitution. And substitution and associativity. We get, and we go for it. C, it's equal to BQ, but B, it's equal to AK, and that is the substitution right there. I substitute B by AK, and here comes the associativity. Right there. There goes the associativity. Just embracing the other two. Right there. And that's it. You know what we have to do. Appeal to the closure of multiplication. Right there. So we can potentially say that the integers are closed under multiplication. Or we could say that the integers have a binary operation under multiplication. Right there. So I can say, see that KQ is in Z because the set of integers are closed, have closure under multiplication, have closure. Under multiplication, have closure under multiplication, right there. Thus, A divides C, right there. We were able to show that C is equal to A times a little cloud, right there. That's why I was doing that associativity. A times a little cloud. So, thus, A divides C as decided. There. Let me give you an example of no closure. One that I did today, let's say with my Calculus 3 students. A vector value function dotted with another vector value function Vx, well, t, respect to t, I'm going to use parameter t like everybody else, yeah, t, the derivative right there, and you don't get a vector value function right there, you get a scalar function, you get a real value function. Well, even with the dot product, you get a real value function. These are vector. I don't need the derivative. Right there, the dot product by itself the dot product of two vector value functions, it's equal to a scalar function, f of t. That's no closure. Closure will be if you take the dot product of two vector value functions and you get another vector value function. And you do not. This is a scalar function or a real value function. There. The ones here look like this. Right there. So today I was working with operations that they didn't have closure. Sets of functions that they didn't have closure under that operation. Okay with that? Okay. If you haven't taken Calc 3, sooner or later, it's nice to explore Calc 3 even for fun. Even if you don't have to take it, just explore it right there. You control your own learning. So, happiness with that. Perfect. So, let me see. There. One last statement. I will not be able to prove it all, but let me write it down. If A divides B and A divides C, comma, then A divides BX plus CY, comma, for some X and Y in Z, right there. So we did one before, that A divides B plus C, but it's actually, this one is slightly more general. It divides a linear combination of B and C. This is called a linear combination. B and C. I'm treating B and C as if they were vectors. And I'm getting right there the resultant of those vectors, but they are not vectors. They are B and C right there. But it's looking that I'm making B longer by multiplying it by X, and I'm making C longer by multiplying by Y, or shorter. Y could be negative right there. So I'm thinking of the linear combination when you add two vectors, but this time B and C are integers. We call that a linear combination anyhow. Right there. Happiness with that? Perfect. So I'll do the jot. I'll do the jot because we don't have enough time. So I'll in full splendor, I put here jot. So it's not a proof, but it's only the strategy. You know that we are going to have this and this. That will provide this for some K in Z, and this will provide A equals to AQ for some Q in Z. This is only the strategy right there. These two, I'll circle them. I circle them right there, and then we bring the expression. The expression is BX plus CY. And we know that we are going to plug in right there. It will be B KA plus C A cube. And then we'll play algebra, factoring. A BK plus CQ. So that's it, we have it. A divides BX plus CY. Of course, I will have to say something about closure. But this is only the jot. I gave you the strategy of the proof, not the proof itself, right there. So for exams, test 2 and beyond, from test 2 on, all the proofs are formal proofs. So this is not a proof, what I've written right now. Happiness with that. So this was example of a jot. No jots on any exams. Okay, let me see there. So I give you the definition of divisibility a little bit early because it's a definition that you need to get used to. Every time you receive a new definition, it takes a while to be able to get acquainted to. And this one is very important, very, very important. So we will get modular arithmetic out of this. We'll be able to just break the integers into classes right there. So it's a very, very important definition. So I must give you super freedom. Super freedom.
2030